Okay, I'll begin. So after my morning lecture, one of you asked me, but where is all the cosmology? This lecture is going to now, in this lecture, we are going to get to the cosmology. And fortunately, Varun set the stage for us in his previous lecture by writing down the redshift distance relationship, which I'll write down again. And it goes as the luminosity distance times the Hubble constant over c. For a change I'm putting in the c explicitly is 1 plus z times the integral over z of the Hubble parameter as a function of z, which is omega m times 1 plus z prime cubed. I'll assume that the space is flat, so I wouldn't put in a omega k. You can put in omega k here if you want, plus omega dark energy or omega lambda, and you can put in a constant if you think it's a cosmological constant, or if you think it's dark energy, you can put in a dark energy equation of state. It can go as now 0 to z prime of an integral 1 plus z double prime of 1 plus the dark energy equation of state parameter. If you prefer, you can then parameterize your dark energy equation of state in some way. So the main thing here is there's everything is a function of redshift on the right-hand side. These integrals may look complicated, but given a value of parameters, what are the parameters here? This and this. You can just forget about this if you take this to be a cosmological constant. And given these parameters, you can evaluate the integral. And on the left-hand side, there's the distance. So if for a large number of sources, if you have a bunch of distances, a bunch of luminosity distances, as Varun mentioned, and a bunch of redshifts, then you can turn the relationship around and measure these parameters. You can come up with the best fit values of these particular parameters. What parameters are we talking about here? The Hubble parameter, the Hubble constant, and all these things like matter fraction, then dark energy fraction, instead of okay. So Varun also mentioned standard candles and standard rulers to measure known brightnesses and to measure known distances. I'm going to introduce another word, standard sirens. And what would be standard sirens? Standard sirens would be exactly like standard candles, but I said gravitational waves are more analogous to, gravitational waves are more like sound. So one just took the word standard candle and replaced the candle with a sound analog of candle, and we call these gravitational wave, the CBCs, standard sirens. Because they give a direct estimate of the luminosity distance to the source. Good. But are we through? Are we done with luminosity distance? What else do we need? We need in order to measure these parameters, along with the luminosity distance, we need a redshift. Exactly. The question is, can gravitational waves provide us a measure of the redshift? So, if the gravitational waves are coming from a binary of black holes, then for a system that has black holes, there's only mass over there. And mass sets an overall scale for the system. And if you just take the mass and replace it by twice the mass, there's going to be a straightforward scaling, and everything is going to go down to lower frequencies. And there is a you can see the scaling if you think about things in the C equal to 1, G equal to 1 units, which I mentioned in the last lecture but didn't quite work things out. It might probably be worth looking at the fact that this whenever we talk about mass, if we think of this quantity gm over rc squared, then this is a dimensionless quantity. So gm over c squared has the dimensions of length, and gm over c cubed has the dimensions of time. So gm over c cubed has time units. When you talk about mass and you multiply by g and c, if these are set to 1, then mass also has time units. So if you double the mass, then the times would also be stretched, and the frequencies would then, the times would become double, the frequencies would become half. So the effect of increasing the mass is just going to lower frequencies for a system that has only gravity in it. There's another way of thinking about it, that it comes from the inertial principle. Putting in a mass is like a gravitational redshift, while putting the thing far away at cosmological scales is a cosmological redshift. There's no way of distinguishing between gravitational redshift and cosmological redshift. That comes directly from the equivalence principle. This is only for systems that are black holes. So for black hole systems, there's no way to measure the cosmological redshift because it is degenerate with the total mass of the system. However, if you have neutron stars, then for neutron stars, there's matter in neutron stars, and the matter shows certain physics at a certain time, and this now is the intrinsic time of this now is the intrinsic time scale, and this can show signatures that this can show signatures that behave like spectral lines. So you know that they occur at a certain time, so they have a certain characteristic frequency, and this is their characteristic intrinsic frequency. If you measure a different frequency, you know that it's been redshifted. So there can be signatures in neutron star waveforms from which you can infer the redshift. Similarly, there can be signatures in the population. You can expect neutron stars to have a certain distribution, and these distribution would be in their intrinsic parameters. If you end up measuring a different set of distribution, then from that distribution you can infer that it's been what the redshift of this system is. However, these properties are not very useful for the current generation of detectors because there's a lot of uncertainty in the populations for them to be used as something standard. The features of neutron star waveforms that I talked about, they are not really measurable to very large, they're not really measurable by this generation of detectors, and moreover, we do not see neutron stars to very far away to make good use of these things. So where else can the redshift information come from? The redshift information can come from an electromagnetic counterpart. So redshift information can come from the physics or astrophysics of neutron stars. And this can be signatures of the wave, signatures in the waveform, or population, or it can come from an electromagnetic counterpart. This can be a transient electromagnetic counterpart. It can be an identified host galaxy or a set of host galaxies. So host galaxies. And there are also methods that exploit clustering properties of galaxies with distributions that we see of binary mergers. Now the question is, which of these can we use in the near future? Waveform properties are probably futuristic. So this is something that's futuristic. This is something that's futuristic, but some people are trying to see if they can actually do something with black hole populations as opposed to neutron star populations. With a counterpart, we have already obtained a result which many of you know about. I'll come to the result in a moment. Sorry. With a transient counterpart, we are exploring the possibility of working with a set of host galaxies using something called the statistical method, which I will describe in great detail. Now on, soon. And these clustering properties is also something that people thought were futuristic, but we still need to question whether all these things that we used to think are futuristic can be made use of in the near future. I'll move on with some slides which essentially have all the information that I wrote down, the redshift distance relation. And this we again heard in Varun's lectures. The Hubble parameter is the slope of the redshift distance relation. What Varun didn't mention is there are two ways of measuring, two state-of-the-art ways of measuring this Hubble parameter. One is using the supernova as standard candles, and there you use a cosmic distance ladder to calibrate these standard candles and eventually measure the luminosity distance to these standard candles and the redshift and get the Hubble constant. And in this effort, you don't want to go very far. You make dedicated supernova surveys only to measure H0 and not the other cosmological parameters. That's the SHOES effort, SH0ES. While you can also infer the value of the Hubble parameter from the CMB. So there you measure the CMB anisotropies, and that gives you the Hubble parameter back at the time of the CMB. And given a cosmological model, you can extrapolate them from the time of the CMB to the current time and get a number for the Hubble parameter at the current time. And these CMB experiments are very, very accurate, so you can still get a very good estimate of the Hubble parameter from these CMB experiments. And these early universe measurements and the local measurements of the Hubble constant currently do not agree. They differ by what is a discrepancy of about 3.6 sigma currently. So, and as you can see, with this discrepancy arose because these experiments over the years became more and more sensitive. These experiments used to give consistent results, but they became more and more sensitive. That's why this discrepancy arose. Now the question is, which of the two is correct? And the other question is, should we really expect the nearby and the early universe measurements to give us the same answer for the Hubble constant given our cosmological model? Or is there anything wrong with the cosmological model? These questions, the answers to these questions we do not know. A good fraction of people think that it's the supernova systematics that is probably going wrong. But whatever it is, an independent estimate of the Hubble constant is going to be very crucial. If you can measure Hubble constant with gravitational waves, as I said, gravitational waves act as standard sirens. You can measure distance directly. You can get the redshift from a number of possible ways. Some of them are feasible, some of them are less feasible. And if you can independently measure the Hubble constant using gravitational waves, and they indicate that they end up converging to the CMB value, then of course something is wrong with the supernova measurements. If they converge to the supernova value, then of course there are two differing, then of course it means that the nearby estimates are giving you the same thing, while the CMB estimates differ. Maybe the cosmological model is going wrong. So low redshift and high redshift here. How low? By how low do you mean low redshift? These redshift, what I call low redshift and high redshift here are very low redshifts, like order of 0.1, 0.2 for the supernova experiments. Let's see how far they go. 0.4, that's not the redshift. This is too small. Does somebody remember how far the supernova experiments go? Nearly up to the redshift 2, but that's for that would be for the Hubble. Okay, up to a redshift 2. But what I mean by large redshifts here are CMB redshifts. So 100, order 1,000. So gravitational wave sources we cannot really see from that far. With our current detectors, we can go up to a redshift of about 1-ish. With future detectors, maybe a redshift of 5. So these would be roughly in the same redshifts as the supernova. Other questions? Okay. Here are some of the methods that I already mentioned. One can use electromagnetic counterparts. One can use information from the physics of neutron stars, like masses or tidal deformations, or one can use angular correlations and clustering properties. Here is the result that we obtained from 1708-17, if you haven't seen it already. So 1708-17 came with an optical counterpart, SSS-17A, which was quickly localized to host galaxy NGC 4993. And for this host galaxy, we could measure its recession, its redshift, and the redshift was because it's very nearby. It's for almost all these galaxies, they're in a field of galaxies close by. So there are corrections to the redshift because of peculiar velocities. The peculiar velocities were estimated and corrected. And after correcting for the peculiar velocity, we obtained some estimate of the intrinsic cosmological recession velocity and the distance, and we obtained a first point in this Hubble diagram. In terms of probability distributions, it looked like this. This is the posterior probability distribution of the Hubble constant, given this, given some prior and this particular measurement. I'm going to talk about these probability distributions and Bayesian statistics in a bit. Again, some of the methods how we can go forward. We can have multiple observations with transient counterparts, and they're going to make this sharper. I'm going to talk about this again in more detail. Now, I'm going to briefly describe the statistical method which is going to useful if you either do not have a counterpart that you can localize to host galaxies. Suppose you see just a GRB that's out there, so you know that it comes from a certain part of the sky, but do not know exactly where it comes from. Then you can look for all the galaxies in that cone, and so these are the possible set of host galaxies, and they have different redshifts. You do not know which one of them it is. Or you just have a sky localization from gravitational waves. With gravitational waves, you can measure the RA and the DEC, and they give you a slightly wider cone, so you have a slightly bigger set of galaxies. It could be any of those redshifts. You do not know which one. If something like that happens, then with a single distance estimate, here's a distance estimate, and this is the probability of the probability density of in distance. And if you have a single redshift estimate, then you should expect a single peak in the Hubble parameter at a certain location. If instead of a single redshift estimate, you have let's say 5 possible host galaxies. So instead of a single peak, you have 5 different peaks. From a totally different event, a totally different observation, it occurs in a different part of the sky, you get an independent distance estimate, an independent set of host galaxies. However, for the value of the Hubble constant, one of these peaks should be roughly at the same location, while the other peaks should be at random locations. If you can now somehow gather the information from all these events together, one of these peaks for all of these events are going to be at the same location, roughly the same location, up to statistical noise, while the other peaks are going to be at random locations. So if you stack them, and I'll talk about a Bayesian way of stacking very soon, then the peak at the right location is going to get enhanced, and the other peaks are going to eventually get suppressed, and you're going to get a nice distribution in the Hubble constant, and this is how the method is supposed to work. Yes. So right now we are talking about measuring only the Hubble constant, and we have left all the other things that we could measure, like matter fraction and energy fraction, fixed to their, let's say, Planck values. If you have one distance and one z, then to the leading order, we are talking about very nearby distances at the moment, so we can approximate the Hubble relation with dl H naught is approximately ZC. So given a Z and a DL, you get one value of H naught. Because of this spread here and this tiny spread there, you get a small spread. If you have a different Z, if you have a Z1, you get a value of H naught. If you have a different Z2, you get a different H naught. No. So of these redshifts, so these are the redshifts of the possible host galaxies. Okay. Let's take a step back and let's look at this. Let's look at this relationship again. H naught is the slope of the distance redshift relationship. Okay, so I do not write down the time dependent h of z. I'm not talking about the time. I'm not talking about the redshift dependent Hubble parameter. I'm talking about the Hubble constant, which is defined locally. So to get this Hubble constant, which is defined locally, what would you do? You would get a set of distances and a set of redshifts. Of course, these distances and redshifts you would not obtain here. With this Hubble constant is defined. This is the slope, so it's defined here. However, these data points, they would be obtained farther away. If you obtain, let's say this is the distance and this is the redshift, you would obtain some point over here with some uncertainties. You would obtain some point over there with some uncertainties. You would obtain some point over there with some uncertainties. So these would not be at z equal to 0. But you would try to fit something through and get the slope. The slope would be at z equal to 0, but these points themselves would not be at z equal to 0. Does that make it clear? Not quite. Okay. No. Okay. Yeah. It would be a single value. Here, what are the different z's that we are talking about? Here, one of them is here. Let's go back to the cartoon I had just before this. One of the here, you do not get a single z here because you have not really seen one unique counterpart whose redshift you could measure. You could localize the counterpart to a certain part. You could localize the compact binary coalescence to some part of the sky, possibly following a GRB, possibly by just gravitational wave localization. So you know that it comes from a certain part of the sky. So it could be any of these galaxies. You look for all the galaxies that are out there. You go back, look at a galaxy catalog that gives you a set of galaxies. You do not know which one of them it is. One of them is the correct one. The other ones are just incorrect associations. Yes. Okay. Yeah. Let us see. I'll remove the statistical bit for a moment. And let's say we have a distance and we have some redshift. This is reasonably bad, this is reasonably good. So this gives us some Hubble constant. Fine. now that's also wide. Let's say we observe something close by. Because it's close by, this estimate is better, so this peak is sharper. And because this is close by, the Z peak is also over here. And because this estimate is sharper, you would get a sharper distribution here. Now, if you take the two of these and combine them together, you would get an even sharper distribution. Fine? This part is fine. So for each of these two gravitational wave events, we have an electromagnetic counterpart. We have an estimate for H naught, and we are combining them. Now, the situation that I'm going to talk about, the situation that I was trying to talk about is when for each of these gravitational wave observations, you cannot really identify a single host galaxy. Maybe you know that it's come from a certain part of the sky, but there is one possible host galaxy here, one possible host galaxy much farther away. Because this host galaxy is much farther away, with just one single event, you are not going to get a distribution like this. You're going to get a distribution like this, and another peak that sort of peaks to the right. I shouldn't go behind the board, I think, but you get this bimodal kind of distribution. Let's say the same thing happens for this particular event. Here, this is the correct host, but you do not know that this is the correct host. You also have an incorrect host that's not exactly here, but a bit close by. So you would get a peak at the right location, but also a peak at a slightly closer location. Now, if you take the information from this and the other one together, then this peak would get very suppressed because there's the tail of, by the tail of this distribution, there's a tail of this distribution, you get a tiny peak. Here everything multiplies just as before, and there's the tail of this distribution, so you again get a tiny peak over there. Fine? And this is an extrapolation to the case where you have multiple such peaks. In reality, you wouldn't see from the number of galaxies that you would see in reality, you wouldn't see these peaks separately. Everything would broaden out to something that looks very uniform, but would still have features in there. And the question is, can we extract features from out of these almost uniform looking distributions? Okay. Other questions? I'll come to the priors and the choice of priors. Okay. So now for some time, I'm going to talk a bit about Bayesian parameter estimation. There's going to be a dedicated course on astrostatistics later on, so this is also going to be useful for that. And this is going to illustrate how this kind of a combining information across events is done in practice, both with the galaxy catalogs that I mentioned, or with the or when we have uniquely identified counterparts. So are most of you familiar with the Bayes theorem? Are all of you familiar with the Bayes theorem? Should I skip it, or should I still write it down? Maybe it's better to still write it down. probability of A given B times probability of B is probability of B given A times probability of A. And this is because this is the joint probability of A and B happening together, and that can be represented as a product of conditionals and a prior probability. Now, if I replace this with, replace A with theta and B with x, where theta is a parameter that we are trying to measure, or a set of parameters that we are trying to measure. And x is the data. Then the Bayes theorem looks like this. So the probability of the parameter given the data, so this is what you the probability of the parameter given the data, since this is conditional on the data, this is something that is called the posterior probability. This is called the posterior probability. So this is what you know a posteriori once you have the data. While this term on the right over here, which is just the probability of the parameters without a data on the right, that is what you think about the data, or what you think about this, the parameter without having seen the data, that is called the prior probability. This term here, the probability of the data given the parameters, how well the data is described by a certain set of parameters, this is called the likelihood. While this term, probability of seeing the particular data itself, is something called it's sometimes called the marginalized likelihood, sometimes called the evidence or marginalized likelihood. And for parameter estimation, this just acts as a constant, while it's very important for doing model selection. So this is the Bayes theorem in the form that we will need it. What are we interested in measuring? We are interested in measuring the cosmological parameters. Let's call them omega. They are the cosmological parameters. This is what we are interested in measuring. So given, so we want the cosmological parameters given a set of observations. This is omega, this x here is gravitational wave data, let's say. This x here is data. And in this Bayes theorem, there are always things that you assume to be true. For example, the underlying model, it can be the underlying model or various other information. And these are things that we always assume to be true. They are always on the right of the conditional probability. So this would be the prior on this. This would be a product of the likelihood times the prior and these probabilities can also be extended to probability densities in the parameter space. Do people know what a probability density is? A probability density, so a probability is a number, and the probability has to be a number between 0 and 1, while a probability density is something which you can integrate over to get a probability. So if you have a variable, if you have a continuous variable, let's call it y. So if you integrate over y the probability density between some y naught minus dy over 2 to y naught plus dy over 2, this will give you the probability of this particular variable being between y naught minus dy over 2 to y naught over dy plus 2. So these probability densities are things that make sense only after an integration with respect to whatever they are a density of. Yes. What are the parameters? Yes. Capital H, so capital H and I are all the other assumptions. And among all the other assumptions, there would be certain assumptions. So I could just have put them into one single symbol. So it's always always important to be aware of the fact that there are certain assumptions that have gone in, and that's why we write this I. And this H here is the cosmological model. I haven't mentioned it. H is the cosmological model. So it could be lambda CDM if you're actually measuring all the other cosmological parameters. If you're restricting ourselves to a nearby universe, then it's just the model that describes the redshift distance relationship as dl h naught as zc. Okay? And for us, the cosmological model can be written down as an expression that probability of dl given z omega h other independent variables is just a delta function in dl. So now this is the probability density in dl that I'm talking about. So it's just a delta function that has a support in the dl as predicted by the cosmological model. Is it clear or is it confusing? This is the dl that is predicted by my cosmological model for certain values of z and other cosmological parameters. So if somebody gives me a cosmological model, a redshift and other cosmological parameters, then I would be able to calculate dl given that model, and it is this number. So the cosmological model asserts that the probability density in dl only peaks at this particular value that the model predicts and at no other value. Omega is the set of cosmological parameters. Let me make it also clear. Omega is the set of all the cosmological parameters that I'm talking here, h naught, omega matter, whatever I'm able to measure. Okay, in terms of practicality, we'll be able to measure only h naught and not omega matter, at least in the foreseeable future. So you can think of omega as only the h naught to make things simple. Omega. We will need to specify omega m, but we will fix omega. If we are not able to measure omega m, And then if we leave it free, then we are not going to get any measurement at all. So what we are going to do is then we are going to fix omega m to some particular value, maybe a value that comes from Planck, and then try to measure the Hubble constant. Okay. These particular bits I'm going to leave because they are going to be important while now these different gravitational wave observations are independent events. So the likelihood of the data, the likelihood of all the data, I am starting from, I'm starting to write this particular term. This is my likelihood. This is my likelihood. This is my prior, and this is my posterior. The likelihood and this X is all the gravitational wave data that we have obtained. So maybe there have been 10 binary neutron star detections. So X is the set of all these detections from X1, X2 up to X10. Fine? And these are independent detections. So if these are independent detections, then probability of X given omega hi, what would happen to this particular probability if these are independent detections? These would factorize. Okay. So for independent detections, the likelihood factorizes as a product of individual likelihoods. And this is how you combine information from different events. You should take the likelihoods from the individual events and you should multiply them together. This is what justified the figure that I was drawing. One very important thing to take care of is when you're writing the final posterior distribution in the parameter space, the prior that you have put in should enter only once. The prior does not. The criticism of a Bayesian analysis is that the final result depends on the choice of the prior. If you change the prior, then the result is going to change. So what prior would you put? You can put some intelligent prior, you can put a lousy prior. If you put in a lousy prior, you're going to get a lousy result. That's, of course, a criticism. But the good thing is, if you have a number of observations, in a large number of observations, and you have put in a lousy prior, with a large number of observations, the likelihood is going to win over the prior, because the prior enters only once, while the likelihood for good data takes you away from the lousy prior and takes you to some peak at a correct value. This is something that I wanted you to appreciate. Okay. Next question is, how do we evaluate this in practice? So these are now my individual likelihoods. Let's look at one of these terms. So this likelihood here, I mean, I'll also write one more statement from probability probability theory. Let me find a good place to write it perhaps over here. Probability of A given B is sum over all possible values of C, probability of A given C times probability of C given B, where C is an exhaustive set of mutually exclusive events. So C is a set such that one of the C's has to be true and only one of the C's is true. So C is a set of, is an exhaustive set of mutually exclusive events. This particular theorem translates to something called marginalization integration in Bayesian data analysis. So given any distribution like this, for a continuous variable lambda, I can introduce this continuous variable lambda over here and integrate over all possible values of lambda. What? I take P of the data given lambda and everything else that was on the right hand side that remains on the right hand side times P of lambda, everything that was on the right hand side still remains on the right hand side, this is the I have opened up this marginalization integration. I have not yet mentioned what lambda is. I'm going to identify lambda with a set of parameters that I was talking in the morning. So lambda is the set of parameters that describe the gravitational wave. So all those 8, 6, 15, 17 masses, spins, they are all the gravitational wave parameters. I call them theta in the morning. Should I switch to theta? Or are you happy with lambda? I'll switch to theta. Now, of all these parameters, it will turn out that some of these parameters are useful for the final result. Some of these parameters enter the final result, while some of these parameters do not enter the final result. So we can divide this set of theta. This theta is the set of parameters. It's a number of parameters. So I'll put on the vector sign, and this is an integration over the entire parameter space. So I will divide this theta into two parts, theta plus, which would be the useful parameters, and theta minus, which would be not the useful parameters. What are going to be the useful parameters? For us, the useful parameters are going to be the redshift, the distance, the locations on the sky, so the right ascension, and the declination. It's usually useful to work in sign of the declination instead of the declination, because the element in the sky is d alpha d cosine delta d delta, so that's d alpha d sine delta. Okay. Write out the integral again. Now I'm going to put in these parameters explicitly. I didn't see these theta minus, the parameters that we leave marginalized over, the parameters that are not necessary for us. In Bayesian analysis, we call them nuisance parameters. They're not always a nuisance, but that just means that they are parameters that are not important for some particular analyses. later? What would you like me to do? Should I go for 5 minutes and come back after the break, or should we take a break now and begin fresh? Let's come back after the break.